Right now, 3 completely separate tectonic plates across our planet are trembling in a terrifying synchronized rhythm. Seismologists in isolated stations are watching their red digital screens spike with unprecedented simultaneous waveforms. Not one fault snapping in isolation. 3 continent-sized slabs of solid Earth are fracturing during the exact same hour. Deep beneath tropical coastlines, ocean trenches, and rural mountain ranges, an invisible tremor is moving our world together. If you love exploring the fascinating realities of Earth science without any sensational fluff or exaggerated clickbait, hit that subscribe button right now. Joining our community ensures you will always stay connected with real, clear, and deeply researched stories about the forces shaping our planet every single day. It began on a warm summer morning on June 24, 2026, when the quiet calm of northern South America was shattered without warning. Deep beneath the coastal mountains of Venezuela, near the vibrant capital city of Caracas, a sudden tear ripped through the ground. Seismic recording instruments thousands of miles away registered a massive magnitude 7.5 earthquake, followed just moments later by a devastating magnitude 7.2 secondary rupture. Buildings throughout dense urban neighborhoods violently swayed back and forth, tearing massive fissures through paved highways and knocking out electrical grids across entire states. Hundreds of thousands of terrified residents ran out of their homes into open streets as emergency sirens echoed against the mountains. The sheer mechanical energy unleashed beneath Venezuela was equivalent to millions of tons of high explosives detonating inside the crust of the earth all at once. Yet as search and rescue teams scrambled to locate survivors in the rubble, a completely separate seismic disaster was unfolding thousands of miles to the northwest. Across the vast expanse of the Pacific Ocean, off the eastern coast of Iwate Prefecture in northern Japan, the ocean floor suddenly lurched downward. Deep within the cold waters, a magnitude 6.9 earthquake tore along an underwater subduction zone at a depth of 50 kilometers. Automated early warning sirens instantly flashed across television screens and mobile phones across Japan, warning millions of citizens that destructive shaking was arriving in seconds. Coastal fishing towns felt the ground roll beneath their feet with intense horizontal shearing force, while sea-floor pressure sensors monitored the ocean surface for signs of an incoming tsunami. Within less than 60 minutes, 2 major global population centers on opposite sides of the planet had suffered massive structural shocks. Before planetary geologists could even absorb the unbelievable timing of those 2 disasters, a third monitoring station in North America began flashing red. Deep in the forested hills of Northern California, near the quiet rural community of Willits, the ground suddenly jolted with violent vertical force. A magnitude 5.6 earthquake had just ripped along a branch of the San Andreas fault system, sending shockwaves through coastal towns. 3 completely different geological regions, separated by thousands of miles of deep oceans and continental landmasses, had experienced major ruptures within the same brief 24-hour window. News outlets across the world quickly began broadcasting frantic live reports, while people on social media started sharing videos of the simultaneous shaking. A terrifying question immediately spread around the world. Was a single global earthquake wave rippling through the interior of our planet? To truly grasp why this simultaneous triple earthquake sent shockwaves of fear through the scientific community, we must first understand how our planet is put together. Although the dirt beneath our feet feels solid and permanent, the outermost skin of the Earth is actually broken into giant, moving puzzle pieces called tectonic plates. These vast slabs of solid rock float on top of a hot, slowly creeping layer of semi-melted mantle rock thousands of miles beneath us. As these massive tectonic plates slowly drift across the globe at a speed of just a few inches every year, they constantly interact along their borders. Some plates smash head-on into each other to build towering mountain ranges, while others grind past each other sideways like 2 giant sheets of coarse sandpaper. In other regions, one heavy oceanic plate slowly dives beneath a lighter continental plate, sinking deep into the boiling interior of the mantle. Because solid rock is rough and full of friction, tectonic plates do not slide past each other smoothly or quietly. Most of the time, the sliding edges of the plates become completely locked together, jammed tight by immense structural friction. However, even though the surface rocks are stuck fast, the colossal heat currents deep inside the core of the Earth never stop pushing the plates forward year after year. This continuous push creates an unimaginable amount of mechanical strain stored within the locked rocks along fault lines. You can imagine a locked fault line like a giant metal spring being slowly compressed by an invisible industrial machine over hundreds of years. The rock can bend slightly to absorb the pressure, but eventually, the force building up inside becomes stronger than the physical strength of the solid rock itself. When that ultimate threshold is finally crossed, the locked rock snaps violently in a fraction of a second, sliding several feet in an instant. All of the mechanical energy that was stored inside the rock over decades or centuries is suddenly released into the surrounding crust. That explosive release of energy creates mechanical vibrations that ripple outward in all directions, which we experience on the surface as an earthquake. Did you know that sensitive seismographs record over 50,000 tiny earthquakes every single day that humans never even feel? Tell us in the comments if you have ever felt the ground shake beneath your feet, and hit the like button right now to help more people discover how the hidden forces of our planet actually work. The force of an earthquake is measured using a scientific scale that many people frequently misunderstand in everyday conversation. When you hear that an earthquake measured magnitude 7.5 on the moment magnitude scale, it is easy to assume it is only slightly stronger than a magnitude 6.5 quake. However, the magnitude scale is logarithmic, meaning that each whole number jump on the scale represents a massive increase in physical energy. In simple terms, every single whole number increase on the earthquake scale represents roughly 32 times more energy being released into the ground. That means a magnitude 7.5 earthquake releases over 32 times more physical energy than a magnitude 6.5 quake, and over 1,000 times more energy than a magnitude 5.5 quake. This explains why small jumps in magnitude numbers translate into vastly greater destruction on the surface. What made the event in Venezuela on June 24th so extraordinarily unusual was that it was not just a single large earthquake. Geologists identified the event as a rare seismic doublet, which occurs when two massive earthquakes of almost equal power strike the exact same geological fault zone within seconds of each other. The first magnitude 7.5 shock cracked open a 40-mile segment of the coastal fault line, instantly altering the stress balance of the surrounding rock. Because a neighboring segment of the fault was already stretched to its absolute breaking point, the sudden shock from the first quake immediately pushed it over the edge. Less than 1 minute later, the second fault segment ruptured with a magnitude 7.2 earthquake, sending a second wave of destructive shaking through the already damaged cities above. The double blow flattened older brick structures, shattered underground water pipelines, and left local emergency services completely overwhelmed. As international news teams gathered in South America to report on the collapse of local infrastructure, updates began arriving from Japan. Off the coast of Iwate Prefecture, seismic instruments placed on the dark ocean floor detected a deep rupture beneath the seabed. Japan sits directly along the eastern edge of the Eurasian plate, right where the massive Pacific plate dives downward into the deep earth at a steep angle. This dangerous boundary is part of the famous Pacific Ring of Fire, a vast horseshoe-shaped belt around the Pacific Ocean where over 80% of the world's largest earthquakes occur. Because Japan has experienced thousands of major earthquakes throughout its written history, the nation has built the most advanced seismic monitoring and early warning network anywhere on Earth. Sensors in the ocean floor pick up initial shaking waves and instantly send automated warnings to cell phones and trains. When the magnitude 6.9 earthquake struck off Iwate, automated systems instantly calculated the depth and strength of the wave within 2 seconds. High-speed bullet trains automatically slammed on their magnetic emergency brakes, safely bringing thousands of passengers to a complete stop before the heavy shaking reached the tracks. Factory assembly lines locked down, gas lines automatically shut off, and coastal communities received immediate text alerts preparing them for potential evacuation. Even though Japan's exceptional engineering prevented massive loss of life, geophysicists in Tokyo were deeply puzzled by the timing of the event. The seabed off Iwate had snapped at almost the exact same hour that the double earthquake struck the coast of Venezuela thousands of miles away. While both regions sit along active plate boundaries, the distance between them is greater than 6,000 miles of solid ocean crust. Before researchers could process the mathematical probability of two independent major ruptures occurring within the same hour, third reports arrived from California. Deep in the quiet hills of Mendocino County near the town of Willits, residents felt a sharp upward jolt, followed by several seconds of intense swaying. Local seismic stations quickly confirmed that a magnitude 5.6 earthquake had ruptured along a branch of the Northern California fault network. This California region is geologically famous for housing the Mendocino Triple Junction, a complex geological intersection where three separate tectonic plates meet and grind against each other. It is one of the most seismically active and unpredictable regions in North America, where the Pacific Plate, the North American Plate, and the small Juan de Fuca Plate are constantly locked in a high-pressure wrestling match. Have you ever wondered if an earthquake happening on one side of the world could actually trigger a secondary fault right under your own home? Write your honest thoughts in the comments section below, and take a quick moment to share this video with a friend who loves solving nature mysteries. When three major earthquakes hit three separate continents within 24 hours, mainstream media and the public quickly embraced a scary idea. Many people began suspecting that a giant invisible stress wave was traveling through the mantle of the Earth, triggering faults like falling dominoes. For centuries, human beings have noticed that natural disasters often seem to happen in clusters, leading to long-standing myths that the Earth enters periods of global shaking. It feels completely natural to believe that an earthquake in one country could set off a chain reaction across the entire planet. After all, if you throw a large boulder into a quiet lake, ripples spread out across the water until they reach every single distant shoreline. Why wouldn't a massive explosion of energy inside the crust of South America send stress ripples through the planet to trigger earthquakes in North America and Asia? To answer this critical question, top geophysicists had to examine two very different scientific mechanisms: static stress transfer and dynamic triggering. Static stress transfer is very easy to picture using simple physical examples. Imagine a group of people standing shoulder to shoulder carrying a heavy wooden beam. If one person suddenly stumbles and drops their section of the beam, the full weight instantly shifts onto the people standing right next to them. When a fault line ruptures during an earthquake, the physical rock shifts position by several feet, changing the mechanical tension on neighboring rocks nearby. This static shift in stress can easily trigger secondary aftershocks on nearby faults that were already near their breaking point. However, scientific measurements show that static stress transfer weakens very quickly as you move away from the epicenter of the original quake. Just like the heat from a campfire drops off rapidly as you walk away into the dark, static stress changes fade to almost zero beyond a short distance. Geophysicists calculate that static stress transfer can only affect nearby fault lines within a distance of roughly 2 to 3 times the length of the original fault break. For the Venezuelan earthquake, that meant static stress could only reach rocks within about 200 miles of the rupture site. Because California and Japan were thousands of miles away from South America, static stress transfer was physically impossible across those immense distances. The shift in physical rock in Venezuela simply could not push or pull on the rocks in North America or Asia. That realization forced scientists to investigate the second and far more intriguing possibility: dynamic earthquake triggering caused by seismic energy waves traveling through the planet. When an earthquake ruptures deep underground, it generates immense vibrations that travel through the body of the Earth and along its surface. Scientists divide these vibrations into two main categories: body waves that travel deep through the interior core of the planet, and surface waves that roll across the outer crust. Surface waves are particularly fascinating because they can travel around the entire circumference of the Earth multiple times before dying out. There are two primary types of surface waves that travel across our planet: Rayleigh waves and love waves. Rayleigh waves move through the ground in an ocean-like rolling pattern, causing the dirt beneath our feet to move up, down, forward, and backward in a continuous circle. Love waves, on the other hand, slice through the ground sideways, shifting the rock back and forth in a sharp, horizontal shearing motion. As these massive surface waves roll across thousands of miles of continental crust, they compress and stretch distant rocks by tiny fractions of an inch. Under normal circumstances, this tiny squeezing motion is far too weak to damage buildings or break solid rock. However, if a distant fault line is already stretched to its absolute limit, sitting on a razor edge of imminent failure, even that tiny nudge from a passing wave can theoretically trigger a break. Scientists actually proved that dynamic triggering is a real scientific phenomenon back in June of 1992. A massive magnitude 7.3 earthquake struck the town of Landers in the desert of Southern California, sending powerful surface waves across the state. Within minutes of those waves passing, small earthquakes began popping up across Northern California and Nevada, hundreds of miles away from the original rupture site. Even more dramatically, after the catastrophic magnitude 9.1 Indian Ocean earthquake in 2004, scientists tracked faint seismic triggering thousands of miles away. Deep in the snowy interior of Alaska, sensitive monitoring equipment recorded a cluster of micro-earthquakes right as the surface waves from Indonesia passed through the northern region. These real scientific discoveries prove that dynamic triggering is not sci-fi, but a genuine geological process. Does it blow your mind that invisible energy waves can travel across entire oceans to stir up distant fault lines on the other side of the planet? Let us know what you think in the comments below, and hit that subscribe button right now to join us for more mind-bending space and earth science stories. So, if dynamic triggering is a proven scientific fact, does that mean the massive Venezuelan earthquake actually caused the quakes in California and Japan? This exact question sparked intense scientific debates at top research institutions like Imperial College London and the United States Geological Survey. Scientists immediately loaded high-resolution global seismic data into supercomputers to trace the exact path and timing of the surface waves. If the Venezuelan earthquake had dynamically triggered the quakes in Japan and California, there would be a very specific scientific signature left behind in the data. Researchers expected to see a continuous path of smaller triggered micro-earthquakes connecting South America to North America and Asia. As the massive surface wave rolled across the ocean basins and continents, it should have set off dozens of sensitive high-pressure faults along its path. However, when geophysicists analyzed seismic records from thousands of monitoring stations across the Americas and the Pacific Rim, that expected path was completely invisible. There was no widespread trail of small triggered tremors rolling across the globe after the Venezuelan shock. The seismic sensors across Central America, Mexico, and the Central Pacific Ocean recorded absolutely normal, quiet background levels during the entire period between the major events. Instead of a smooth wave of falling dominoes, scientists saw 3 isolated, completely independent ruptures, lighting up on the global map. If the surface wave from Venezuela had been strong enough to push a fault in Japan over its breaking point 6,000 miles away, it should have easily triggered thousands of weaker, closer fault lines along the way. The total absence of those intermediate quakes pointed scientists toward a very different conclusion. The clear conclusion reached by global experts is that this terrifying triple event was almost certainly a pure mathematical coincidence. While that answer might sound less exciting than a secret planetary wave, the actual mathematics behind global earthquake activity are far more shocking than most people realize. Our planet is in a state of continuous, restless movement, constantly grinding out earthquakes every single minute of every day. According to long-term statistical data compiled by the National Earthquake Information Center, Earth experiences around 20,000 recorded earthquakes every single year. That means an average of 55 earthquakes strike somewhere on our planet every single day, year after year, without stopping. Furthermore, our planet experiences an average of 16 major earthquakes measuring magnitude 7.1 or higher during any given 12-month period. When you have thousands of active fault lines around the globe constantly building up immense strain over decades, it is mathematically guaranteed that occasionally 2 or 3 major faults will reach their breaking points at nearly the exact same moment. It is just like flipping 3 coins in 3 different rooms. Every once in a while, all 3 coins will land on heads at the exact same second purely by random chance, without influencing each other at all. Were you surprised to learn that 3 massive quakes thousands of miles apart can happen at the exact same time purely because of mathematical probability? Share your thoughts in the comments section below, and hit the like button right now to support honest, clear science education that cuts through internet panic. To truly understand why statistical clustering happens on Earth, we need to look deep inside the fiery engine driving our planet from the inside out. Thousands of miles beneath the peaceful towns of California, Venezuela, and Japan lies the core of the Earth, a scorching sphere of liquid iron and nickel hotter than the surface of the sun. This immense thermal furnace continuously heats the surrounding mantle layer, forcing dense hot rock to slowly rise upward toward the surface over millions of years. As this heated mantle rock approaches the underside of our solid crust, it cools slightly, spreads out horizontally, and slowly sinks back down into the deep interior. This continuous circular motion, known as thermal convection, acts like a giant planetary conveyor belt that slowly drags our solid continental plates along with it. It is this relentless, unstoppable internal heat that keeps the fault lines of the world under constant strain every single minute of the year. Because this thermal engine has been running nonstop for over 4 billion years, the outer crust of our planet is locked in a state of permanent tension. Fault lines everywhere are perpetually accumulating mechanical stress, like thousands of individual clocks, ticking down at different speeds. Eventually, several of those independent clocks are bound to strike midnight at the exact same moment, creating the illusion of a single, connected global event when viewed from the surface. This continuous release of energy is also why scientists pay close attention to historical seismic sequences to see if current patterns match the past. Throughout recorded history, human beings have documented strange clusters of catastrophic quakes that made entire civilizations believe the world was ending. For example, in 1811 and 1812, a sequence of 4 massive earthquakes struck the New Madrid fault line in central North America within a span of just 3 months. Those historical quakes were so immensely powerful that they temporarily forced the mighty Mississippi River to flow backward, turned solid ground into liquid mud, and rang church bells hundreds of miles away in Boston. Yet, even during that historic series of violent shocks, geologists later confirmed that the ruptures were isolated events taking place on a single local fault complex rather than a global chain reaction. The Earth was simply clearing decades of built-up tension along a single weak zone in the continental plate. Do you find it fascinating how our planet recycles its internal heat to move whole continents over millions of years? Write down your thoughts in the comments section right now, and hit that subscribe button to keep discovering the incredible physical forces that shape our universe. Right now, geologists and disaster response teams are actively monitoring fault lines across all 3 regions to see what is happening in the aftermath. In Venezuela, emergency crews and scientific teams are tracking over 30 aftershocks that continue to shake the Caribbean coastline. Aftershocks are smaller secondary earthquakes that occur as the disturbed crust slowly settles into a new stable position following a major rupture. In Japan, marine geologists are continuously analyzing deep sea pressure sensors off the coast of Iwate Prefecture. Because Japan sits directly above a dangerous ocean subduction zone, Scientists must closely track depth changes to ensure no larger slip is developing deep underwater. Luckily, the magnitude 6.9 event produced no dangerous tsunami waves, but continuous real-time monitoring of the ocean floor remains active 24 hours a day. Meanwhile, in Northern California, seismologists are analyzing precise movement data from the San Andreas Fault Network to track how strain was redistributed. California experiences several moderate earthquakes every single year, and each event provides researchers with critical data about how tectonic energy shifts through North America. Modern space technology has revolutionized how scientists track these movements long before an earthquake ever strikes. Using specialized satellite systems known as interferometric synthetic aperture radar, or INSAR for short, scientists can measure tiny shifts in the ground from space. These satellites beam radar signals down to the Earth and compare the reflected images over weeks, months, and years. This technology allows geophysicists to track ground movements down to a fraction of an inch, mapping exactly where structural strain is building up in real time, long before a fault snaps. In addition to satellite radar, global seismic research facilities like the Lamont Doherty Earth Observatory are installing deep subterranean borehole sensors directly inside active fault zones. These hypersensitive instruments are lowered thousands of feet into solid bedrock, shielded from surface noise like traffic, ocean waves, and wind. They can detect microscopic creaks and tremors deep inside locked faults long before the rock actually gives way, offering unprecedented windows into the mechanics of rupture. Understanding these powerful geological processes matters deeply to every single person living on our planet today. We live on a dynamic, living world whose hot core drives the movement of continents, builds our highest mountains, and creates the very land we build our lives upon. Earthquakes are not signs that our planet is broken, but clear proof that Earth's internal heat engine is active and full of energy. By studying how strain builds up inside locked rocks and how seismic waves travel through the mantle, scientists are constantly improving early warning technology. In places like Japan, California, and South America, modern sensor networks can detect the very first non-destructive compression waves of a quake and send automated warnings seconds before the violent shaking arrives. Those extra seconds allow high-speed trains to stop, gas grids to close, and families to take cover. Furthermore, advances in structural engineering and architectural design are saving countless lives every single year during major seismic events. Modern skyscrapers in high-risk zones are now built with giant internal shock absorbers, flexible steel frames, and pendulum counterweights that absorb seismic vibrations. These brilliant engineering innovations allow giant towers to sway safely during violent shaking without collapsing onto busy streets below. The simultaneous shaking in Venezuela, California, and Japan serves as a powerful reminder of how interconnected our human experience really is. Even though we are separated by vast oceans, different languages, and distinct cultures, we all share the same thin crust of rock floating above a restless planetary forge. Respecting the raw power of Earth and seeking real scientific truth helps us build safer communities, protect our loved ones, and appreciate the incredible world beneath our feet. Now we want to hear your thoughts. Do you think humanity will eventually invent technology that can accurately predict earthquakes weeks in advance? Or will the interior of the Earth always keep us guessing? Drop your answers in the comments right now because we read and reply to your thoughtful opinions every single day. If you enjoyed this deep dive into real planetary science, please hit that subscribe button, turn on all notifications so you never miss an upload, hit the like button, and share this video with someone who loves exploring the mysteries of our planet. Thank you so much for watching, and keep exploring until next time.